This is the 11th installment of the Crash Course Regents Chemistry Review Series, and this is a tour of the reference tables. My goal is to remind you of where things are on these tables that you'll get for the Regents Chemistry exam coming up. I have the current edition, and again, I want to remind you where things are, what information are at your fingertips, not to leave questions blank or wrong because you didn't know where to look, and a little review of the problems that can result from each of these tables, some more than others. So let's get started with reference table A. Let's be crazy and go in order. Alright, so we're starting with A, and A lists some important pieces of information that come up mostly in our gas law problems. You'll hear the word maybe not that, you'll hear the word STP. So STP. STP is standard temperature, standard pressure. Standard pressure comes in kilopascals and in atmospheres. Standard temperature in 0 degrees Celsius and 273 Kelvin. So these are synonymous. They measure the same pressure using different units. Same thing goes with the temperature. Now, when you're dealing with a gas law problem, they say at STP. I got a lot of students that say, I don't have enough information. But by them saying at STP, they're reminding you you're dealing with these values. Be careful. If it's a gas law problem, you're going to be dealing with 273 Kelvin and of course one of these two pressures. Now, which one do you use? You use the one that is already started. So if I have a gas law problem that says, hey, I have 2.3 atmospheres at a certain temperature or pressure, and now I want the new volume, let's say at STP. If I'm starting in atmospheres, okay, I have to be in atmospheres so they cancel out. If I start you in kilopascals, you have to put the kilopascal one there. So standard temperature and pressure, there's the values, okay, if you need them. At STP, they're applying about these values. Let's go to table B, okay? Now table B is physical constants for water. These values come up in calorimetry problems, and they're tied specifically to a place in table T. So let's go to table T for a second. In table T, lists a bunch of different chemical equations, I should say, not chemical equations, but equations to use. And these equations that I'm looking at are specifically for heat or thermal energy. We have Q equals mc change in T, and this is the heat measured when you have a change in temperature. Specifically, it's going to usually be a liquid. And notice the change in temperature. The C, they tell you, is specific heat capacity, and this is the mass of the water. So when you use this form, it's the mass of the substance, specific heat of the substance, change in temperature of the substance. That substance is usually going to be water, as you did in calorimetry problems. And you should know, my friends in chemistry here, that when you have a change in temperature, if you look at a cooling and heating curve, let's just draw it pretty roughly as I'm doing, we see that this is the liquid phase, solid phase, gas phase, and when you have a change in temperature, okay, MC change in T is where you would use if you've got a liquid phase. If you don't have it, and it's because you have a change in temperature. Now, if you're at a phase change, in this case, it's a solid going to a liquid, or in this case, a liquid going to a gas, you know that those temperatures stay constant, and kinetic energy, which is the y-axis, doesn't change, and you can measure that phase change. We know that to be true because kinetic energy is converted to potential. But what formulas do we use here? Well, if I'm fusing or melting, it's mass times heat of fusion here. And if I'm vaporizing or condensing, it's mass times heat of vaporization. They don't have a temperature change, so you have to use the constants. And table T tells you what these things stand for, but table B gives you the values of these three things for water so that you can plug them in. So if a problem says, hey, I have 100 grams of ice, how much energy does it take to melt it at its melting point temperature? They're screaming a phase change, and I would take my 100 grams and I would times it by the heat of fusion. Or they said if I have 100 grams of water and I want to freeze it, how much energy has to be released at the freezing point, which is the same as the melting point. It's the same problem. Here, if I had 100 grams of water and I said how much energy does it take to completely evaporate, boil off 100 grams of water at its boiling point, 100 times that. And then I would use a specific heat capacity, which you've learned is nothing more than a value that tells you how well a substance will change its temperature I'm stuck with this formula, mc change in T. So if I have a liquid changing 20 degrees, I know its specific heat capacity, that goes here. How many grams of that liquid, or usually that's water here because it's all about water, I can find total energy change. Now, this table B has implications for things other than water. Obviously this is water, so if you don't have water, they have to give you different constants. Now, one more piece of information here. You should realize the heat of vaporization, this is a big Regents question or concept, heat of vaporization is always larger than the heat of fusion, always. And the reasoning behind that is that if you're making a liquid go to a gas, there's a tremendous change of potential energy. Gases have unbelievable amounts of kinetic energy compared to liquids, so they need more, liquids need a lot more energy to make this happen. Solids who have very little motion have more motion as liquids, but nowhere near the potential energy change occurs for liquids going to a gas compared to a liquid going to a solid going to a liquid. So there's a tremendous potential energy change here. So there's a lot of energy that needs to be absorbed. And if you know, if you look back on my drawing, my heating and cooling curve, they love to ask this too. This line right here is always longer. The what? The vaporization or condensation line is always longer than this line here, because this value, right, you're absorbing energy at a constant rate, takes a lot more energy, okay, to vaporize. So this length of this line is longer. Okay, very important concept. Table C. Table C is a list of prefixes used for the metric system. So you should know that kilo means 1,000, deci means a tenth, 1/10, right? Centa is 1/100th, okay, and milli is 1,000th. And even they have micro here, 1 what? Millionth, 1 over 10 to the 6th, 1/1,000,000th. And you got micro is 1/1,000,000th, nano is 1/1000,000th, 10 to the 9, and pico is 1/1,000,000,000th, 10 to the 12. Okay, very small values. So I've yet to see yet to see really any conversions with these values, but I guess it's fair game. You never know. So case in point, you've seen most of your conversions go from these values here. But let's pretend we had a new question. It may say, hey, if I've got 35.3 grams of something, convert to micrograms. Well, as you've been taught probably in your class, get rid of your grams. And I want micrograms. Micro is 10 to the negative 6. So I'm going to use just a little m. Hold on. I can do this. Okay, I'm just doing a little mg, microgram. Okay, it's a little funky m actually, but it doesn't matter. And I know that for every one of these, there's a huge amount of these. In fact, it's 10 to the 6, 10, it's a million. So I would just divide, actually times that. Okay, so for every 1 gram, and you would times by a million, which is 6 zero places, and this number is going to get bigger, 3, 5, 3, and you're going to move 1, 2, 3, 4, 5, because it's going to be a total of 6 decimal places, and this would be milligrams. Okay, so you say, my gosh, that's a big number. Why did it get bigger? Because we're going to a smaller unit. And if you don't like how I did this, I don't like moving decimal places left and right. I like to use my units. I know that the bigger unit is a gram. Milligram is a tinier unit. It's a millionth. It takes a million of those for every one. The bigger unit, smaller what? Number. The smaller unit, bigger number. How does that work? Well, I'm a pretty tall person if you don't know who I am. And if you measure the length of Grodsky, okay, and you measure the shortest person in the class, and you measure the length, let's say, of this table, let's say it's a life-size table, okay, it takes less Grodskys. A bigger unit will take a smaller number. So that's how that works. Now, I haven't seen any of these conversions, but again, I guess it's fair game. Okay, most of the conversions I see are from kilo to milli, okay, which is 3 decimal places. And those that love to move decimal places, be wary. Okay, if you're going to move a decimal place, if you're going to make a number into a smaller unit, Okay, if you're going to move a number into a small unit, it better get bigger for the same reasoning. So if let's say I had 3.5 liters, and I want to convert that to milliliters, which is a classic way we would go. Well, milliliter, there's 1,000 of these for every one of these. Bigger unit, smaller number. So I'm timesing by 1,000. Now some people don't like this, they want to fight me on this. Okay, so I'm moving this 3 over, and this of course is milliliters. And if you're going to make a what? The unit goes smaller, the number has to get bigger. Notice it got the value, the integer got bigger. And the opposite is also true. So in any case, these are conversions moving forward. I think I meant D, the next table. Any case, D is selected units that are used for different values. These are essentially going to be the SI units, the units that we use internationally, selected units. But if you need to know what a symbol is and what the unit is, it's given to you here. Of course, meter is the unit of length, gram is the unit of mass. This is not an SI unit because kilogram is the SI unit for length. They're just giving you the symbols for what we measure. Pascals is a unit of pressure. Of course, Kelvin is temperature. MOL, look at that abbreviation. Took off the E. Good for you. Made that so much smaller. Kind of like taking the I off of Mississippi. Wow, thanks for the memories. Any case, so mole is mole. MOL is used to abbreviate mole, and we use joule for energy, time in seconds, minute, hour, day, year, so forth. So these are just some symbols. I don't ever recall any kind of question with these. But if you didn't know what ppm stand for or what the big M stood for, these things are some helpful units that may be helpful, like a part per million. Maybe big M you forget is molarity. Molarity is helpful, and that equation is given to us in table T. A little u is atomic mass units. Any case, this might be helpful. Let's move on to table E. I call E the what the heck is that table, because table E, okay, inevitably has a bunch of cluster of atoms that people don't know. Like if I had sodium and I had this, some people when they first learn chemistry, what the heck is all of this stuff? How am I supposed to know what this is? And I always tell my students, if you run into a what the heck scenario, usually it's a polyatomic ion, a cluster of nonmetals. So it's not really what the heck is that anymore at the end of the year, but initially when you start looking at these things, you say, what the heck is this cluster? It's a chromate. And polyatomic ions are used for many different things, but number one is naming. And when you name a salt, an ionic compound, because these things are charged, you name them. It's the name of the metal in front or the chemical in front, sodium. I don't care how many you have, and the name of the polyatomic ion. So this is just sodium chromate. And if I had sodium with permanganate, guess what? Sodium permanganate. So the naming is very simple. These are salts or ionic compounds. They're called ternary compounds, and they're also electrolytes. These things will break apart into ions. So these clusters of nonmetals will attract metals. So this could be sodium nitrate, NaNO3, as you've seen. And these will break apart into Na plus and this is NO2, I guess, the nitrite ion. And what's special about polyatomic ions is they have a scenario, as I've talked about in other things, that inside the polyatomic ion, because they are nonmetals, inside the polyatomic ion between the nonmetals is covalent bonds. And you should know covalent bonds exist between nonmetals because they both have high electronegativity. They're forced to share. Okay, so these are covalent bonded. So within the polyatomic ion, you've got, okay, normally between the nonmetals, a covalent bond. And then between the ions, you have ionic. So polyatomic ions have both covalent bonds and ionic bonds. Okay, so anytime they're asking for both, you're looking for something with a cluster of nonmetals in a salt compound, in an ionic compound. Now, also learn that ionic compounds, and a lot of people talked about ionic compounds as metal and nonmetal, but you can have a scenario where you have a bunch of nonmetals. Ammonium is a positive polyatomic ion, okay? And let's say nitrate's a negative. So I could write what? NH4 NO3. And there's no metals anywhere around. So when you learn that, hey, an ionic is metal, non-metal, not necessarily. There are cases, and far and few between than the others, but there are cases where you can have just what? A positive polyatomic ion between another negative, right? This is the positive one. Okay, this is the negative one. So, well, it was a negative one before I got rid of it. Okay, so there it is in all its glory. something to think about there as well. Also, an acid and base, some people confuse hydronium with hydroxide. Hydronium is a water holding onto a proton. It's responsible for acidic environment, low pHs. Hydroxides are responsible for more basic, higher than 7 pHs. Okay, something else to think about, acetate ion. People forever would ask me, Mr. Grodsky, which acetate ion do I use? Well, my friends, in chemistry, the acetate ion is nothing more than what we'd say is the conjugate base of an organic acid. You guys learned that a Cu group, okay, is an organic acid. Well, if you lose that H, okay, you're an acetate ion. Now, people say, well, which one do I use? Well, my friends, in chemistry, they're the same. This is a molecular formula, and this is a structural formula. So you could use either one. Okay, one is showing the bonding because this one's organic. We learned structure is king in organic chemistry. And this one is showing how many overall. Okay, very simple stuff here. And if you see a cluster of nonmetals and don't know what it is, it's probably listed in table E. I've seen questions where people had didn't know how to name something with an O2 ending, a peroxide. So if I had sodium peroxide, Na2O2, you'd see that that peroxide O2 ending is also a polyatomic ion. That's essentially what we have here. Anytime you need a cluster of nonmetals, need a name for that, or naming, understanding covalent and ionic bonds occur here, we've got them listed here for our viewing pleasures. Table F. Okay, well, table F, okay, gives me the solubility guidelines for aqueous solutions. This tells me how well something will dissolve. And they love to phrase the question, who has more free ions? Who has more dissolved ions? Who is more soluble? Okay, and they'll give you a couple of salts, and you're going to have to evaluate them usually in table F. Now, very simple to use. This is ions that form soluble compounds. For instance, let's zoom in here. Let's get up close and personal with this. Okay, and if you're in this column, you are ions that can form soluble compounds. And if you have group 1 ions, you're always soluble. There are no exceptions. So if you have anything with a potassium in front, you are soluble and make free ions. If you have ammonium ions, if you have ammonium chloride, ammonium fluoride, doesn't matter. If you've got ammonium, you're always soluble, no exceptions. Nitrates, acetates, hydrogen carbonates, all the same. Chlorates, all the same. Now, halides are normally soluble, and so are sulfates, but there are some exceptions. The exceptions are written right here. So if you've got silver chloride or silver bromide or silver iodide, you are insoluble. If you are calcium sulfate, strontium sulfate, barium, or lead-2 sulfate, okay, you're also insoluble. So these guys are soluble normally. Here are the exceptions. Okay, and it works the opposite on this side as well. Here, we're insoluble compounds. And notice they have bigger charges. Usually if you're insoluble, you've got big charges. That means that the ions would rather stick together than interact with the water, but that's something for another day. But all you got to read is if you got carbonates, like carbonates, you know they're insoluble, except there are some exceptions. Like for instance, if you got a group 1 in front, so if I have sodium carbonate, that thing is soluble because of the group 1 ion. So it kind of makes sense that it's working with the rules already established on this side. Okay, so these, but if I have, let's say, calcium carbonate, well, that is insoluble because calcium is not one of the exceptions. And you can see how to read them. So same thing goes across. Notice your hydroxides, okay, are insoluble except with group 1 and these 3, and these actually are your strong bases, and with the ammonium. So again, insoluble, there are some exceptions. All right, and again, that's all you have to do for those types of questions. And you'll hear people say, or you'll hear questions say, which of the following salts has the most free ions, the most soluble? When you're comparing them, you're going to go to this table. Okay, table G could also be a place where you go to identify who is more soluble, but you're going to hear something special at table G. You're going to hear temperature. You're going to see how much water, so grams of water will be given to you, and also grams of the solute particle. So you're going to hear a lot more information when they want table G. They're going to say who is more soluble at a certain temperature, okay, in in a certain amount of water. And that's going to clue you into table G question, because for those that don't remember, this table is based upon all 100 grams of water. This y-axis is how many grams of stuff you have trying to be dissolved, and the x-axis is temperature. Okay, so that's how that table works. Now, there's a couple of vocab words associated with this table. If you're on the line, we call that saturated. If you're below the line at a particular temperature and amount of water, you're unsaturated. And if you're above the line, we call that supersaturated. Okay, and what kind of questions arise here? Well, there's many different types. We can compare the solubility of certain different solids or gases. And for instance, I could say, who is more soluble at 50 degrees Celsius, SO2 or potassium chlorate? Potassium chloride's here, SO2 is here. Of course, potassium chloride's more soluble. It can have about 22, 23 grams of potassium chloride that can be dissolved in 100 grams of water. This is all based on 100 grams of water at 50. Now, if I was to ask you, let's pretend that this was 22 grams here. And we're going to say that if I have a saturated solution of potassium chloride at 50 degrees Celsius and 100 grams of water, if I boil off the water, how many grams would I recover? I'd recover 22 grams. But what if I said I'm saturated and I have 50 grams of water? I would cut my answer in half. This 22 grams is based on 100 grams of water. So this table is always based on 100 grams of water, but the question states in 50 grams of water, you'd have to cut that in half, and the answer would be 11. Okay? Now, what other questions could you see? There's a whole myriad of questions here, but they all associated with the three terms. So let's just say I have 10 grams of potassium chlorate at 50 grams in 50 degrees of water. So I have 10 grams. And they said, well, how many grams do you need to make it saturated? Well, you would just measure that you would need, in this case, 12 grams. Okay. What if I had 10 grams at 50 and now I heated to, let's say, 80? Well, if I heat it, I know that solid solubilities go up, and now I'm here. Let's make that 44. So I was at 10, now I go 10, 20, 30, 34 grams would be necessary to make it saturated. Now I can go the other way with this. I can make something supersaturated. So we're going to stay on our 50 degree, this is 50 degree line. And let's just say at 60 degrees Celsius, I've got a saturated solution of potassium chlorate, and it cools to 50. Well, the solubility drops. How much comes out of solution? How much is going to precipitate out of solution? Well, now when it drops, now I'm above the line, I'm supersaturated, which means I'm going to come out of solution eventually. So you go 5, 10, another 5. We would say 20 grams would recrystallize. We did a lab like that. Okay? So some other words or some other variables in terms of vocab words we would use for this table. Okay? And generally speaking, they could give you the word concentrated. Concentrated just is a general term that says a lot of solute particles compared to water. So anything in the top 2/3 of this table is considered concentrated. And it doesn't have a number associated with it. Okay? Whereas anything in the lower, I should say lower third, is generally speaking going to be dilute. Dilute just means you have a small amount of material compared with small amount of solute being dissolved in water. And those are the basics of this curve. You're going to hear temperature, you're going to hear grams, you're going to hear how much grams of water, I should say, how much water you have, and that's important because this graph is based on 100 grams of water, and then grams of solute, and the use of the word concentrated, dilute, and concentration and dilute will be used, and you'll hear the word supersaturated, saturated, and unsaturated to describe the solution. Now, one more piece of very important information that this graph loves to show us is that most of these lines tend to go up. So I'm going to get rid of some of this. Most of these lines tend to rise up. Why? Well, most of these lines are solid solutes. You should know that solids, their solubility increases with temperature, whereas gases' solubility decrease with temperature. They love to ask. We have 3 gases where the lines are going down. So the least soluble of the phases in water are gases. You increase the temperature for a gas, its solubility goes down. Look at the curves. And it makes sense. Gases have very weak intermolecular forces of attraction, especially if they're ideal. All right? So they have high kinetic energy to begin with. You give them more energy, more temperature, they're going to go even faster and escape the liquid. All right? Something that this chart does not talk about, but it's implied as well, the solubility of a gas depends on pressure. If you have a gas in a liquid, higher the pressure keeps the gas from leaving. So gases are more soluble, very important. Gases are more at lower temperatures and higher pressures. Okay, moving forward. Table H is an important table, and it reviews vapor pressure and how liquids differ from each other. Vapor pressure is the rate of evaporation. Nice easy way, rate of evaporation. Why? Well, if you have a liquid, it's going to eventually, if it has enough energy, some of these already do because temperature is a range of movement, will escape into the gas phase. And they'll create a particle moving up, creating a pressure. If you increase the temperature, more molecules have enough energy to overcome the attractive forces and the vapor pressure goes up. So the first thing you need to know from this table, temperature increases, increase in temperature, and the temperatures in the bottom, these curves go up. Temperature is directly related to the amount of vapor pressure or the amount of evaporation. That's absolutely important. Now some liquids evaporate much faster than others. Now why? Well, the ones that evaporate faster have weaker attractive forces, and you should know this is an important core concept. The ones that don't evaporate as fast have stronger attractive forces, like they resist evaporation. The boiling point is when the pressure upward from a liquid equals the pressure pushing down from the atmosphere. So if your atmospheric pressure is standard, when we use the word normal to talk about boiling points on standard conditions, we know when the vapor pressure upward hits this dotted line, it's now reached standard pressure, and I can go find that temperature. And for this acetone, it's 56. Okay, for ethanol, it has a higher boiling point, about 74. Why is it higher? Because it has stronger attractive forces. The ones with higher boiling, look at water. This is water right here. It boils at 100. And it resists evaporating compared to the other two because it has a lower vapor pressure at any one temperature and it has stronger intermolecular attraction. So you should know, okay, higher the boiling point, okay, stronger the attractive forces, right? And lower the vapor pressure. It's important concepts here. Now, if I lower the pressure, let's pretend I'm a princess, which I'm not, and I lower the pressure to, let's say, 50. Well, acetone, which normally boils at 56, now is going to boil at a much lower temperature. This is 30, 35, maybe 37. So its boiling point dropped. You lower the pressure, okay, the vapor pressure doesn't have to be as high to overcome a lower pressure. And if I raise the boiling point, and of course this happens on the top of a mountain, the boiling points are lowered, but if I raise the boiling point, okay, if I raise the pressure above, the new boiling points are going to be higher. So many questions on here is, hey, what's the new boiling point of water? Water usually boils at 100 when the pressure is 100, if now the atmospheric pressure is 50 kilopascals. Well, if it's 50 kilopascals, water is now going to boil, water now is going to boil right here. And did I put 74 here? This would be, I'm sorry, I don't know why that's 74 there. So if I said 74, bad, 79. But for water, it'll boil approximately at, 84, 85, right? 75, 80. This is 70, I can do this. 80 is here, 85. So let's an 82 and 83 here. So on top of a mountain, water boils at a lower temperature. Okay? So if I gave you the pressure to be higher, okay, you just read that temperature. So it's very simple. Vapor pressure equals the atmospheric pressure when it boils. All right, moving forward. Table I gives us a lot of information. First and foremost, it tells us and reminds us what combustion reactions are. The top third of table I are all combustion reactions. Some kind of fuel with oxygen, okay, gives us usually CO2 and water, and very exothermic here. So we're burning something. We're burning. Okay, delta H is exothermic. What does that mean? That means that we have less energy as reactants. I'm sorry, as products than reactants. And why? I'm drawing a potential energy curve. Why is it lower? Because energy was given off. We have the reactants, okay, and here are the products. So here's the reactants are more what? Unstable than the products. They have higher energy. They're going to do something. They can burn. They can explode. So potential energy curves are going down, and the difference of where you start and where you finish is delta H, and they're all negative because the energy is dropping. And if you forget that, the bottom of this table tells you that a minus sign indicates an exothermic reaction, which means energy is released. So if you look at the values here, if I was to give you these reactions, and a lot of times with table I questions, they give you a bunch of reactions, say who's exothermic, and you can't look at a reaction and know. You need the delta H. If they put the heat here, which would be 890.4, notice I'm just putting the heat where? On the product side, because if it's exothermic, energy is being released, it's being lowered, the energy has to be on the product side. If it was endothermic, which combustion is not, like this is positive 182, this would have to be 182.6 plus the energy goes on the reactant side. Huge, important understanding there. Now, why is this positive? Well, it's because that we started here with my reactants, okay, which is N2 and O2, and we became products, which are NO2. And the products have more energy than the what? The reactants, and the energy level, okay, increased. How much did it increase? 182, because that's how much it gained. Difference of where you start and where you finish, okay, is your delta H, or that fancy word enthalpy. So in these types of questions, what they do is they first, well, they could give you reactions and say, is it exo or endo? They could say, who has greater amount of energy? The reactants or the products? Well, if it's exothermic, you start high and you go low. The products have lower energy than the reactants because you're going to ignite something. If it's endothermic, it's the other way. Another place where they use this table is they could say, hey, how much energy is given off per certain moles or grams? For instance, this 890 amount of energy given off is per 1 methane. If they said, hey, if I had 2 moles of methane, how much energy is released? Well, then it'll be 2 times this number, because these values are molar quantities. In the bottom of this table, it says that the delta are based on molar quantities, based on the balance reaction. For instance, if we go to octane, gasoline, for every 2 of these, that's how much energy is released. So if they wanted it per 1 mole, you divide by 2. Or if I have 0.8 moles of propane, how much energy is released? Well, this is per 1. You can do a proportion or just times by 0.8. Very important. The middle third are formation reactions. This is the Regents' attempt to make a heat of formation table. Okay, so these are all synthesis reactions or formation reactions from their elements, and when they're formed from their elements, they're either made endothermically or exothermically. Okay, now I haven't seen these questions in a long time, but you can compare actually the bonds. If something is exothermic and more exothermic, like for instance gas to liquid, who is more stable? Well, the one that gave off more energy is more stable. So the more exothermic you are, usually the lower in energy you are, which means stable. So you can compare the strengths of bonds by how much energy is released. Obviously, if you're absorbing energy when you make something, you're making something more unstable. So if I was going to compare C2H4 and C2H2, and I wanted to know who has stronger bonds or who's more stable, I'd pick C2H4, and the reason is because it has a delta H that's closest to being negative. This is more unstable. And by the way, C2H4, doesn't that have 2 bonds? isn't that going to be stronger than one bond, C2H6, which is an alkane? This is unsaturated. Kind of makes some sense. Ooh la la. Now, careful with these questions because sometimes they'll ask for the reverse. If this is a formation reaction and this is negative 84 in the forming of C2H6 ethane, they could ask for the decomposition. And you should know from potential energy curves, the reverse, the forward is exothermic, the reverse is positive 84. So they could ask for the delta H of the reverse reaction or the decomposition of these things, and you have to reverse the signs if they ask that. Now, in the bottom of this table are ionization reactions. These guys are salts being dissolved. They're all soluble. But when they dissolve in water and make free ions or electrolytes, sometimes they make the temperature of the water go down and make a cold environment. Why? Endothermic reactions take energy in. This is endothermic. This energy has to go on the reactant side. KNO3 takes energy from its environment to do this, so it's endothermic and the environment gets colder. Sodium hydroxide, when you dissolve in water, okay, gives off energy. So this makes a warm solution. So a lot of times they could ask you, hey, how do I know something is endo or exothermic? Well, if I know the temperature drops, that must mean that something is absorbing energy, right? The chemical here is taking energy from the water anytime we have an endothermic process. So you'll see those questions. Lithium bromide and sodium chloride. Which one is going to make the water warmer? The exothermic reaction. This reaction is going to release energy to the water. This will make something colder. Okay, so you have to know something exothermic makes the environment's temperature go up. Something endothermic makes the environment's temperature go down. Why? Because the chemical, in the case of NaCl, is going to absorb energy from the environment, right? If you don't quite get that, okay, look at my drawing here. Okay, I want to draw myself a beaker of water, and I have a reaction in here. Let's say it's endothermic reaction. I know that by a positive delta H. So if I have sodium chloride dissolving, endothermic means it's going to absorb energy from the water. So if the water loses energy to the chemical who needs it, in this case NH4Cl, the temperature has to go down. And the opposite is also true. If something's exothermic, it releases energy into the water. Okay, the frame of reference is who is responsible for changing the temperature of the water. It's the chemical. And that's what we do here, moving forward. So table J lists the activity series of metals. And you know metals lose electrons, and losing electrons is oxidation. Nonmetals gain electrons, and that's reduction. And so we use this table to decide who's better at losing electrons. And we'd see that lithium is the best, rubidium is second. As you go down, you can see that metals are less active. Okay, now how do we use this? Gold doesn't like to lose electrons, that's why it doesn't rust. Now how do we use this table? Well, we use this table to usually decide if we're trying to find an anode or a cathode. We know anox, so if we're trying to find an anode of a electrochemical cell, or specifically a voltaic cell, we're going to try to find the metal that's higher than the other. So if I got magnesium and cesium, okay, the anode would be the cesium because it's better at oxidizing. So to find out who's the anode in a voltaic cell, see who's higher. Now another way we use it is in figuring out if a reaction is spontaneous. Can it work? For instance, okay, if I have, let's say, strontium trying to replace calcium chloride in a reaction that's going to make strontium chloride and let's say pure calcium back, that's a single replacement, it's a redox reaction. I want to know if this works. We say, well, is this spontaneous? Spontaneous means, does it work? Okay, so what we do is, if the strontium is above the calcium, and it is, strontium is better at oxidizing, so it must oxidize. Well, this is going from 0 to +2, so clearly it's going to oxidize. Standalone elements always oxidize, so if this is spontaneous, the one who's better at oxidizing better be oxidizing, and it is. So this works. The one who oxidizes will be above the one who's involved with reduction. And that's how we determine. Now if I wrote it the other way, and I had calcium here and strontium here, well that won't work, because strontium, if it's going to work, should be the one oxidizing. Okay. Now, another thing that we use this for is figuring out if we make hydrogen gas. Okay, and it's tied to the standard cell, but we know that the standard cell where all these things were compared with was from this reaction. Now, truthfully, we have two H pluses plus 2 electrons equals H2. All right, now, if H plus is going to, 2 H pluses are going to get reduced to make hydrogen, we need something who can oxidize to do this. So that means that anytime I'm making hydrogen gas, or if I do make hydrogen gas, I need all the metals above to get what? Oxidized. Oxidation is above the one who reduces. So anytime I'm trying to figure out which metals will make H2 gas, I do that by doing it that way. So if I have nickel and I have hydrochloric acid, will it make H2 gas? Is this spontaneous? Well, if you look very carefully, hydrochloric acid gives off H pluses, and it becomes 0. So that means that the H plus is going to get reduced, and nickel is going to oxidize. Now, if nickel is better at oxidizing than H2, if it's above, this will work. So and of course, this is spontaneous. So all of these metals above H2 would mean that you'll produce hydrogen gas. If I was to plug in gold or silver or copper in these positions, they would not make hydrogen gas. And that's essentially how we use this table. Now, there's a little piece to this above, and we have nonmetals. Now, nonmetals, okay, react by gaining. So this is really showing who's the best at reducing. And of course, fluorine is the best at getting reduced, I should say. And fluorine's the best here. Okay, and of course, if you have reactions with these guys, fluorine, who's better at reducing, better be reducing, and the chlorine better has to oxidize. Okay, so there have been a few occasions where the activity series is used here, where they have a reaction where the fluorine, chlorine, and bromide are the principal elements that are involved in passing around electrons. So if you have a reaction between these, the fluorine or the one above it has to be the one who's reducing. Here it's the one oxidizing has to be above the one who is reducing. On this side, it's the one who is reducing has to be the one who's oxidizing. And the real reason behind this is net potentials this table is based on. So if you've got a reaction of nonmetals, okay, and you want to figure out if it's spontaneous, the one who's better at reducing better reduce. Okay, and it's basically how it works here, but it's based on a list of oxidizing moving forward. I guess the best way to explain this, if I have F2 and Cl2, what are they going to make? Well, do I make ClF or do I make FCl? This is a 0, this is a 0, this would be a -1, this would be a +1. This, of course, would have to have a 2 in front. This would be a +1, this would be a -1. Who got reduced and who got oxidized? Well, according to our table above here, F is above Cl. So F should reduce. So its charge should go down. So this 0 should go to a negative. And the chlorine, which is not as good at reducing, it should be oxidizing, is going up. This would be the answer. So this would be spontaneous. Okay, so I've seen questions like that. Let's move on again. Table K is all your acids. Okay, and these are all Arrhenius acids, as written with H's in front because they produce protons. CO2 by itself, maybe not an Arrhenius acid if you give it CO2 because it doesn't have an H to give off. Okay, so ethanoic acid, all these have the H's in front, are example of your acids. So if you're given a name of an acid you don't know, look at table K. Very simple. Now table L is a common basis. Bases you should know or usually are salts. There is a negative polyatomic ion and a positive. Okay, and they all have this. What is not a base is alcohol. So if I have CH3, which is what? A rest on organic molecule and an OH, it's not a base. Okay, very important. Now NH3 is a base even though it doesn't have an OH attached to it. So these three are Arrhenius bases because they produce hydroxides as the only thing in solution. This thing grabs an H from water and indirectly produces an hydroxide. So this is the other definition, which is called Bronston-Lowry. You don't have to know it by name, but when you have NH3 in water, this thing with a lone pair can accept an H plus from water and produce NH4 plus, that's the ammonium ion, and the hydroxide. So indirectly it creates a basic environment. And by accepting an H, it's acting as a base, and by water giving off an H, it's accepting as an acid. So this comes from the other definition, you're responsible. These are Arrhenius bases, this one's not, doesn't have hydroxide. Table M, the indicator. Okay, these indicators are nothing more than weak acid-base pairs that change color based on what physical shape or how their structure changes. But what you have to know is that if I have methyl orange, if it's 3.1 or lower, okay, we're red. 4.4 or higher, we're yellow. Anything in between is a color in between, which could be orange, but they don't like to ask that one. Bromothionyl blue, if I've got a pH of 3, which is less than 6, it's yellow. I've got a pH of 8, it's above 7.6, it's blue. If I've got a pH of 7 or 6.8, it's probably green in between. Phenolphthalein is pretty much colorless below 8. Everything above 8 starts to get pink. Okay, litmus, of course, is red below 4.5, blue above 8.3, and of course there's a color in between, but that's not going to be asked. It's like a peachy color, but people think it might be red, blue, purple. Brome crystal green, yellow to blue, in between is green. In between these two is green for the same reasons. So they talk about an indicator. They said, hey, which of the following makes litmus turn blue? Well, we're talking about a basic pH, so you're looking for a base. If I say, which of the following make bromothionyl yellow, I'm looking for something less than 6 or 6 and lower. That's an acidic range. I'm looking for an acid. And it really is that simple. Table N is our radioisotope, or our nuclear chemistry table. It tells us the types of elements, specifically the form of an element called an isotope that is radioactive. And it gives the half-life, which is the amount of time for half of this substance to decay into something stabler. It gives the decay mode, which is the type of particle it emits, which, by the way, is given in Table O. So in Table N, when they give you the particle, B negative, here is beta particle. And they tell you it's a mass. Mass number is up top, charge number is in the bottom. Notice this guy has less mass than an alpha particle. But to figure out what these symbols mean, okay, let's say from Table N, Table O is your friend there. Getting back to Table N, okay, we have our half-lives. What you should know about your half-lives is things with shorter half-lives, okay, are much safer than things with longer half-lives. Why? Because things with shorter half-lives decay into something stabler faster. A lot of it will decay. So if you have something with 8.51 minutes half-life, if you have 100 grams of it, it takes only about 8.5 minutes for 100 grams to become 50 grams of something stable. So 50 grams of the radioisotope is left. If you have something with 5.27 years half-life, it'll take that long to take to have 100 grams turn into 50 grams of something safe. So obviously things with shorter half-lives decay into amounts that approximate 0 much faster than these things. These will stay around longer and be dangerous. These things very quickly, okay, will become safe. All right, so, and of course things that have shorter half-lives, okay, are what we use for medical diagnosis. Okay, and that's how we use this table. So if you need to know a half-life for a half-life problem, type of emission with Table O, okay, Table N is your friend in many nuclear chemistry questions. Table O. Table O is probably my most favorite of all tables, especially in atomic structure. If you've been with me through many of my videos, people don't use it. They tend to use it only at the end of the year, but it is very helpful to know is the difference between a proton, neutron, electron. If you forget, neutrons have a mass of 1, it's the mass number, they have no charge. Protons have a mass of 1 and a charge of 1. So you can see that neutrons and protons have the same mass. Now they don't write it here, but this used to say electron. Electrons are beta particles, and they have a mass of 0. Now, and a charge of -1. In truth, their charge is about 2,000 times lighter than a neutron or proton. They put a 0 here because its mass is insignificant. Gamma radiation has no mass and no charge. That's why this has the greatest penetrating power. Alpha particles have a mass of 4, big and heavy, and a charge of +2. These have the least penetrating power because they're so heavy. Okay, and a positron is nothing more than a positive electron. It's that antimatter. Again, if you need to know the specifics of what's going on, Table O is your friend. Okay, so Table P gives us the prefixes to name organic compounds, like C3H8. I have 3 carbons in my chain, so it starts with a prop. If I had 4, it's a but, and so forth. So these tell me how to name things based on the longest continuous chain. Very straightforward. Table O is a very important table. It shows me who's a saturated and who's an unsaturated hydrocarbon. Okay, so alkanes, the family homologous series that have single bonds between them, okay, are ethanes. Okay, eth is 2 carbons from table P. Ane is for the bond in between. These are saturated. These are important. They're holding on to the maximum amount of H's. If I was to what? Take a bond and add a bond between the carbons, I'd have to lose two H's here. That's why I lose 2 H's in my formula. So this is CnH2n plus 2 if you're saturated. If you have a double bond, it's double the amount of H's per 1 Cn. We lose those 2 there. And if you add another bond, you lose even more. So your CnH2n becomes CH2n minus 2. So these guys are unsaturated. It's important to know your hydrocarbons in terms of their saturation. These things will make addition reactions because they'll add into the entire chain. These make substitution reactions because they have no more room. Okay? Like saturated fats are single bond, unsaturated or polyunsaturated have more than one or have double or triple bonds. Moving forward. To appreciate table R, you have to be around for a while because there was a time when you had to memorize all of these functional groups and all of the different types of naming ways. Now they give you the general formula and they give you how to name each one of these. And I spent a lot of time on table R in my crash course for organic chemistry, but just going to remind you that the general formula means the rest of an organic molecule. So here's the rest. If I have CH3, which is a hydrocarbon, and I have a Cl attached, there's my R, and there's my halogen, the X. So the general form is the rest. Now, alcohols are not what? They're not bases, they're not electrolytes, and here is the R. The R is on this side. And they tell us how to name these things. The OL is for the alcohol. The ether is measured around the single bonded O on both sides. And they give you an example of how to name. The AL ending is for the aldehyde, and that's the CHO ending. So very important place to look when you say, hey, what kind of organic compound this? The one they pick on the most, the organic acid, that's the COO group, the COOH. It's an organic acid, so therefore it's an electrolyte. Okay, it's an ending, so it doesn't have a number. And they pick on the esters. In esterification, we should know that an organic acid made this compound. It's a propanoic acid. And an alcohol, we split the O's to figure out the alcohol and the acid part. But again, here's an example. They give you an example how to name them. They give you the formula here and the name of them. So much good information to know where that is. And the R represents a bonded atom or a group of atoms. Normally, I always call it the rest of an organic molecule, hydrocarbons usually. Moving. Now, the periodic table of elements is self-explanatory, how you use it. However, people forget they give you some information. Atomic mass is here for 12. Electron configuration shows you how many electrons exist in each energy level, 2nd and 4. And they give you the oxidation states that exist for that element. Okay? The possibilities of when they become an atom. You should know that all atoms listed or elements listed in this table are atoms, which mean they're all electrically neutral, which means this number here, the atomic number, is also the electron number. So if you need to know number of electrons in an atom, it's the protons equal the electrons. When they become ions, they gain electrons to become negative because you're what? You're gaining negative charge, or you lose electrons to get that. So it's important to realize how we use that table, and of course it's all listed here. Here are your ions, here is the number of protons or electrons, here is the arrangement. Also in your periodic table they give you the group numbers. Now the group numbers, okay, the group numbers tell you also valence electron, 2 valence electrons, right? It's very important you know that. And also you can differentiate between metals and non-metals. Not going to spend a lot of time here. But these are your metalloids. They have properties of both metals and non-metals. And your non-metals are over on this side. And your metals are over here. They're bigger atoms. Talked a lot about them in other crash courses. Okay? And you can differentiate between who your gases and who your solids. Okay, your gases are here and here, and your two liquids, or your your gases are here and here, and your two liquids, or your bromide and your mercury. Everyone else is a solid. So there's a little basics and stuff to look for here. Notice the period number is the row number is the principal energy level as well. Okay, a lot of information given there. Understand that the electron configurations, as I think about this, are always in their ground state. Okay, so these numbers are in their ground state. Okay, so the excited state is never given, always given as an atom, protons equal electrons, and always in the ground state. And of course, you should know the top number is your mass number, and that's the average of all the isotopes that exist in nature with the abundances. So I could ask you, what is the most abundant isotope of calcium? And you would say calcium 40. Why? Because it averages to 40, right? That means 99% probably of all calcium is calcium 40. What's the most abundant isotope of chromium? You would say chromium 52 for the same reasoning. One of the most underutilized tables is table S. Now table S gives you the symbol with the atomic number with the name. Some people say, how do I know Ne is neon? I don't know. Table S is there, so you've got a symbol and you don't know the name of the element, you've got it there in table S. First ionization energy is the same thing as ionization energy. It's the amount of energy it takes to pull an electron away. Nonmetals like hydrogen, okay, or carbon, nitrogen, oxygen, they have very high ionization energies because they hold on to electrons tightly. They're nonmetals. Metals have low ionization energies because they lose their electrons. So the amount of energy it takes to pull an electron away is called the first ionization energy. Now the second would be to pull the second electron away after you pull the first. So whether you talk about ionization energy or the word first, it's the amount of energy it takes to pull an electron away. Electronegativity, of course, is the attraction for electrons. Nonmetals have high electronegativity because they attract their electrons. That's why they are small. Metals have low electronegativity because they don't attract the electrons. That's why they're big. Melting points are listed. Be careful, they're in Kelvin. Boiling points are listed for the elements. Be careful, they're in Kelvin. Density is listed in atomic radius. Knowing the smaller atoms are going to have the higher electronegativity and the higher ionization energy, and that's the trends. So information specifically about elements is given in table S. Be sure to utilize that correctly. And then we're left with table T. And table T is nothing more than a table that gives me the formulas for things. Density, if you need it, is written. Mole calculations, going from moles to grams, maybe. I don't ever think about using this one. Percent error. They could ask you to do a percent error, and it's the measured value, the experimental value that you get from the experiment minus the accepted, the theoretical, over the theoretical times 100. Percent composition is part over total times 100. And concentration, we have the molarity formula and the part per million formula if you need it. We have the gas law formula. We have the titration formula for acid-base titrations. And then we talked about the heat already, and then converting temperature into Kelvin. So that's a little bit of a tour through the periodic tables. I hope that was helpful to help you remember where there's information that could possibly help you on this test. Good luck. See ya. Rock on.